Okay, so if I define the distance between these 2 points as some d, then d is nothing but 2 times a. Or alternatively, I can say that a is d divided by 2. Does this make sense? Why am I looking at the distance between the 2 points?
The shorter distance will be the correct distance.
Your audio is not very clear, Harsh.
Because we are working on minimum distance decoder for
Exactly. We are working on minimum distance decoder. Very good. And so a lot of the times we are going to be focused on what is going to be the decision rule, or what is going to be the performance of my decoder. So decision rule is always going to be dictated by minimum distance between 2 points. And so it's good that we start thinking about this constellation diagram in terms of what is the distance separation, Euclidean distance separation between the 2 points. The other interesting part is that you see on the previous slide here, we derived the expression for the error probability as Q of A divided by sigma n, but this I can also write as Q function of, in terms of distance, Q function of distance between the 2 points. But remember, A is half of the distance, so I can write it as 2 divided by, sorry, D divided by 2 times sigma n. So if I do it like this way, then I have kind of removed the notation A here. And I'm firmly looking at what is the distance separation between the 2 symbols. Sometimes this view is going to be helpful to us. So remember this equation that I have written here. Okay, so with that, we drew the constellation diagram of BPSK. We also saw what the diagram looks like at the receiver in the presence of noise. And it basically kind of becomes fuzzy. At the transmitter, we have 2 clean points, the 2 transmitted symbols. At the receiver, each received symbol is a noisy version of the transmitted symbol. And depending on how much noise voltage the channel introduced, you can get these red points which are kind of all over the place. And then we can actually look at any one of the received points along this diagram and then draw 2 vectors, one connecting to the positive symbol, another connecting to the negative symbol, E1 and E2 in this diagram. And then simply say which vector has a smaller length. That becomes essentially the minimum distance decoder. And that also allows us to quickly see that all the blue points here, all the received points on the positive real valued axis are going to be always closer to +1. All the blue points which are on the negative side, meaning the voltages received are negative valued, are going to be closer to a symbol for the bit 0. Okay, so this is the basic concept that we had reviewed last time. And we saw that the theoretical error probability is this Q of A divided by sigma n, which again is Q of the distance separation divided by 2 sigma n. And the good thing about this expression is that this is purely theoretical expression. It doesn't care about what you have done in the FPGA or in the VLSI chip or in your MATLAB program or Python program or Java program. It doesn't care about any of that. This is purely a mathematically derived expression of the bit error probability of a BPSK demodulator. And so what this allows us to do is, if we write a program or if we implement a BPSK modem, we can actually connect the transmitter to the receiver in the presence of real world channel, maybe in the lab or maybe in the factory setting somewhere, and then see how many bits we are getting in error in some controlled environment. The reason I say control is because we would need to know what the transmitted bits are. Then we will get the received bits and we will compare the transmission with the reception, and we can calculate maybe in Excel or Google spreadsheet how many bits are correct, how many are wrong. And that way we can determine what is the bit error probability. And then we can also change either the distance separation or the sigma n, the variance of the noise, the standard deviation of the noise. And for each value of d divided by 2 sigma n, we would measure the bit error probability and compare it with the theoretical answer. Hopefully, all the blue points which are empirically calculated or experimentally derived for different values of a divided by sigma n should match the theoretical expression, which is Q function of a divided by sigma n. Now, you all have just come out of the high school and this is your first year of engineering school. So obviously you wouldn't have this perspective. But let me tell you, because in fact, before joining this college, I was in the industry for a number of years. And you would be amazed to hear from me that just on this particular slide, there are tens of thousands of engineers who have spent sometimes their entire career, maybe 10, 20, 30 years of their work life is on this type of graph. Why do I say such a strong statement? See, there are a lot of things that we take for granted, right? I mean, when we get a Wi-Fi router at home, when we get a set-top modem for our set-top box, satellite TV, or when we start using a Nokia phone or a Geo phone or Samsung phone, we don't realize the intricacies of the engineering design. Before those phones or those modems reached us, there are countless number of engineers who would have worked on making sure that the product that reaches us is working well. And at the lowest level, at the most granular level, what is the definition that the product is working well? It is exactly this chart. If the modem sitting inside your phone or your set-top box or your Wi-Fi modem or router, if it generates bit error probability which matches nicely with the theoretical curve, the rad curve, as it is shown in this model, then everything is fine from an engineering point of view. But sometimes what will happen is these blue points, instead of lining up nicely like this, they will be like this. So let me see. Okay, I'll draw the blue point in the rad only for the time being, but maybe let's say the blue points are like this. You see, for different values of SNR, my blue points are actually showing performance which is far worse than what the theoretical expression shows. And so if I connect this all by dotted line, is something like this. And in case if your modem exhibits a performance like the one that I have drawn, it means that your design is not working well. So when I say that there are literally tens of thousands of engineers who have worked and who continue to work on this type of graph, what I mean to say is there are engineers who come up with ways of having hardware in the Samsung lab or in the Nokia lab or in Xiaomi's lab, which generate Gaussian noise with programmable sigma n. So they make equipments that we have never seen. I mean, I have seen it, but you have never seen. The equipment is just generating the Gaussian noise. But you can dial the level of Gaussian noise. It is generating the Gaussian noise in a controlled manner. And so you can, in the laboratory, using the real hardware of your phone, you can generate an experiment which allows you to control this A divided by sigma n. And so therefore you can go along this x-axis, you can go from 0 to 10, and then do this type of bit error rate plot. Then there are other set of engineers. Actually, when I say engineers, these are actually startups that have become standalone companies. So this other company would have a controlled environment where the transmitter bits are prepackaged. Maybe the transmitter will generate 10,000 or 1 million bits. The receiver will also record those bits. And this company is in the business of making an equipment which will connect the transmitter to the receiver and compare the bits that have been sent. And that way it will calculate the values along the y-axis, the bit error probability. There are companies which allow you to change x-axis, the SNR, or there are companies whose equipments allow you to measure the bit error rate in the laboratory. And so using such equipments manufactured by different companies, the modem engineer of, let's say, Nokia does this type of test. And then if the performance is so much poorer compared to this theoretical red line, then his boss and his boss's boss, they get angry. They say, oh, you haven't done a good job. You are not a good Java programmer or a Python programmer. Either you repair your problem or we have other engineers who will take over your code. Maybe I'm simplifying a little bit here, but the point is that is how the entire design evolves. And so what you are seeing here in a classroom setting has a real world repercussions. I mean, this is some real heavy duty engineering that is kind of abstracted out in this particular slide. Okay, you may not see the faces of people here. You may not see the emotional investment that people have in making sure that their designs, their engineering designs, and the supporting equipments, the equipment that measures the bit error rate, the equipment that allows you to control the sigma n, all of this together allow you to get the final product which is working as expected. Okay, so that is some practical real world perspective that I thought I'll give it to you. Now, coming back to our subject topic, the actual concept behind this type of performance evaluation studies. One thing that you will notice is that based on this theoretical expression, that the performance depends only on the ratio A divided by sigma n. This we have, I think, talked about repeatedly. That the absolute value of the received signal doesn't matter. The absolute value of the noise also doesn't matter. What matters is the relative aspect. How much is my received signal stronger compared to the noise, which is captured by this ratio A divided by sigma n. A is the received voltage, sigma n is the standard deviation of the noise. And a lot of the times, instead of writing the performance as A divided by sigma n, this is written as this, what is known as EBNO in all of what is this engineering slang, EBNO. It's actually EB divided by N naught. EB is nothing but energy per bit. Okay, so that part is clear. EB is nothing but energy per bit. Energy per bit. And for BPSK, each bit turns into a symbol. So only for BPSK, EB is also same as energy per symbol for BPSK. Or even for, oh, okay, that is the case. So EB and ES are interchangeable for BPSK, maybe not for some other schemes that we will look at now. Okay, so EB part is clear. Now, remember we said that energy per bit or energy per symbol is nothing but the squared Euclidean distance. And so EB is nothing but A squared. And so this ratio A divided by sigma n, I can replace A with square root of EB. Is it fine? The reason I'm doing that is that sometimes this voltage value A is not as how should I say it? The energy is more of a common engineering concept rather than the voltage. How much energy you are spending is probably sometimes more important, right? I mean, when you get your electricity bill at the end of the month for your home, the bill calculates how much energy you have utilized, right? So energy is kind of more commonly used engineering concept. So we would replace A with square root of EB. Now there is one concept that we will very briefly look at later on. For the time being, you just take my word for it. It is that sigma n is something called n naught divided by 2. So we are just introducing new notations. Okay, these are not terribly important things to do right now, but we will kind of get going on this so that later on our notations become more aligned with what is commonly used in the industry and in the academics as well. So sigma n is n naught divided by 2. What is n naught? N naught is something called the power spectral density. Okay, so you will ask, what is power spectral density? So that, just wait, I will talk about it. And so once I write it like this, then you will obviously see that this same equation here that I have written as Q of A divided by sigma n or Q of D divided by 2 times sigma n, I can also write it as Q of square root of 2 times EB divided by n naught. And so a lot of the times x-axis is this EBNO or EB over n naught, which is nothing but A squared divided by 2 sigma n squared, as we have just now seen. And this is just nothing but signal to noise ratio, except this signal to noise ratio is over 1 bit. We are not kind of collecting signal to noise ratios over multiple bits. For each bit, what is the signal to noise ratio? That is what EB over n naught defines. More accurately, I should say energy per bit to the noise ratio, but then it becomes a little bit cumbersome terminology. In general, it is called SNR per bit. Okay, so this is kind
Sigma
of
square is, so sigma square would not be n naught by 2.
sigma square will be n naught by 2. Yeah, correct. So this is wrong writing. This should be sigma n squared is equal to n naught by 2. Correct. Okay. So now that we are hopefully clear on the basic concept that this, what we have been calling the simplified model has given us, we can now kind of expand our vision, right? With this concept that hopefully you have grasped, you can now do bigger and better things, okay? So basically you do some thought experiments and say that, what if I come up with some different modulation schemes? Let us say somebody wants to define a modulation scheme where bit 0, which is in yellow, is transmitted using -3 volt, and bit 1 is transmitted using +2 volt. Somebody else says that I want to transmit bit 0 using 4 and bit 1 using 6 volt. And yet another scheme would be what we have already seen. This is the standard BPSK. Bit 0 is -1, bit 1 is +1. Now, the principle of minimization of Euclidean distance is like a very general principle. It holds no matter what your scheme is. And so regardless of the schemes, whichever constellation diagram is given to you, without doing any Bayesian mathematics, you can right away say that at the receiver, my decision boundaries are going to be halfway between the 2 points, as I have shown here. Why is this the case?
Transmitting both the bits are independent of each other. 2 equals 2.5.
So, Bhavya, you are not audible. You have to bring your microphone closer.
Because Q equals to 0.5.
Correct. Yeah, okay, fine. That's a very good point. Here we are assuming that Q is equal to 0.5. Bit 0 and bit 1 are equiprobable from the transmitter side. So then why is the RAD boundary, decision boundary is halfway?
Only then the minimum distance decoding will be possible.
Yes. So Jmesh correctly said, or Deep, I don't know, Deep or Jmesh, what is your name?
Deep, sir.
Okay, Deep. So Deep has correctly pointed out that only when we draw it halfway, then our Euclidean distance minimization will take effect. What about the performance of the schemes? Can anybody say anything about that?
Scheme 1 might have the best performance among the three.
Scheme 1 might have the best performance among the three. Yes. What about the exact mathematical expressions?
Sir, for scheme 1 A will be 1.5. That's why.
Yeah. Instead of A, maybe start thinking it in the terms of D. And so D is going to be 5 for scheme 1. For scheme 2 and
For the
scheme 3,
distance,
it's going to be 2 volts. And just as we said that the principle of minimum Euclidean distance holds irrespective of where the constellation points are. Even the performance also depends only on the distance between the points. It doesn't matter what their absolute locations are. Right? If two cars are traveling on the road, and maybe this is a very poor analogy, Just bear with me. So if two cars are traveling on a road, and let's say the drivers are not very careful, then the probability of the accident happening, basically these two cars colliding, depends on the distance between them. It doesn't matter whether these two cars are on a highway near Gandhinagar or a highway near Surat, right? So the absolute location doesn't matter. And so therefore we can say that the probability of error for scheme 1 is going to be what?
Less compared to the other two schemes.
No, I'm asking for the exact expression. Q function of
Q function of 5 by 2 sigma n.
5 divided by 2 sigma n, or 5 divided by square root of 2 n naught.
Yes.
For scheme 2 and scheme 3, it will be just 1 divided by sigma n. So obviously, scheme 1 will perform better. Okay. Now, along with the notion of energy per bit or energy per symbol, there is something called average energy of your design, average symbol energy or average bit energy. So what is going to be, let me call it EB average for this constellation? What is the average energy for scheme 3?
2.5 square.
No, scheme 3.
1.
A square, so
Huh?
1. 1.
So yeah, Deep has correctly said this is just 1 because bit 1 is transmitted with an average energy of 1 joules, and bit 0 is transmitted also. -1 squared is 1. So average energy is 1. What about scheme 2? What is going to be the average energy of scheme 2?
Also 1, sir.
25.
Sir, one. Sorry, one.
Average energy per symbol or average energy per bit for scheme 2.
25, sir.
EB
30.
average for
30,
scheme
sir.
2.
Should it be 30, sir?
No?
30.
Yeah, it is going to be 30. Why it is going to be 30?
Because it's for
It's not going to be 30.
186 square.
No. 30 is not the right answer. Sorry.
26.
Close to 30, but not 30.
26.
26.
26.
26. Yes, we are. It is 26. Now, if you are the designer, and remember this energy per bit is a concrete concept. If you are talking on your phone for 1 hour or 2 hours, I hope you don't do that, by the way, but maybe some of you are talkative, and when you get in your groove with your friend, you keep on talking over and over, longer and longer, and maybe what will happen is your battery will drain out, the phone battery. And so as an engineer, you want to make sure that the phone battery lasts longer. Now, what is phone battery? It is nothing but energy storage. And so if you are transmitting each bit using only 1 unit of energy, then compared to scheme 2, for which you transmit 26 units of energy, you are going to be more energy efficient. And so you may wonder that, okay, I'm spending 26 times more energy for scheme 2 compared to scheme 3. But what am I getting in return? In terms of the performance, in terms of whether the users hear disturbances or they hear clean voice, scheme 2 and scheme 3 gave me identical performance. And so, is there any reason to do scheme 2?
No, sir.
No.
Yeah, so Krunal is correct. There is no reason to do scheme 2. It has no benefit over scheme 3. And it is in fact hurtful compared to scheme 3 because you're wasting energy. Okay, now I'm going to ask you a question which I would like you to think about and answer quickly. Is scheme 1 the best possible scheme that somebody can come up with, or there is some other smarter scheme which gives the same performance as scheme 1, but it is better in terms of...
We can change 2.5.
Half point at 0.
Plus or minus 2.5.
But we can choose the scheme 1 to be centered around 0.
Correct. So what we would do is we will just slide these 2 points, and instead of this red boundary away from 0, we will make it at 0. And so as somebody said, this yellow point will go to minus 2.5 and this will go to plus 2.5. And you see this came just because, I mean, you were able to give this answer quickly because the concept is clear in your mind. You didn't even do any energy calculation. You didn't calculate the energy of scheme 1. You didn't calculate the energy of this alternate version of scheme 1. But intuitively, you would think that this alternate scheme 1, which I have drawn here, handwritten, will have smaller energy compared to this original scheme 1. But its performance is going to be identical. It is going to be same as this Q function. So then again, why would you do scheme 1? So this kind of should give you an idea of why BPSK is a popular modulation scheme. Compared to scheme 3 or scheme 2 or, compared to scheme 2 or scheme 1, you can convert both of these schemes, scheme 1 and scheme 2, into a BPSK version of it, which is always centered at 0. And it is always going to be more energy efficient than the other alternatives, while it will give the same performance. Does that make sense? So,
Yes, sir.
So you see that there are some conceptual understanding that we can get by just focusing on what is ultimately driving the performance of our system. Okay. Now,
Hello, sir.
before we proceed, I will take a small break, and then we'll go over the remaining topic for today. So remember we introduced this notation of N naught. And we said that N naught is called the power spectral. N naught is the power spectral density of the white noise. And so what is this power spectral density and what is the white noise? Well, what engineers and researchers have found out many years back through the actual laboratory experiment that they would do in the with the real hardware is that at a communication receiver, if they disconnect the wire and just look at the signal that is coming from the air, being just the white noise, just the noise, sorry, then that noise has equal power no matter which frequency you are looking at. And that is sort of like what the white color that our eyes see is like, right? And from your physics course in your high school, you would know that the white light that our eyes see is a combination of all the colors. All the colors are equally present in the white light. And also you would know that each color is a different wavelength of electromagnetic spectrum. Right, so red is at the smallest frequency, and blue and violet are at the higher end of the visible spectrum. And so if I want to focus only on one part of the visible spectrum, let us say red, then I can kind of put a filter that kind of blocks out all the other colors, all the other frequencies of the visible spectrum that our eyes can see. And that filter will only allow me to see the red color. And so if I'm looking at a particular scene which has nothing colored in red, then I will see just dark image. I will not see anything. And you can buy such filters in the market. They are nothing but your specially made goggles. So these goggles will be like acting as filters, which will allow only the specific portion or specific frequency segment of the electromagnetic spectrum to go through, and everything else will be wiped out. Except if you are looking at white color, then what will happen is if you use a particular goggles or particular eyeglasses which blocks out all the frequencies except red, and now you are looking at white background or white color, then you will see actually not dark, you will not see black, you will see red color, because red is the only part of that white light which is coming in through that goggles. Now, think about what I said. I don't know whether you understood what I said or not, but later on, before the end of the semester, maybe 1 or 2 weeks before the end, we are going to spend some time on the topic of Fourier transformation. What I just said is highly intimately connected to Fourier transformation. And even more, we are going to look at the filters that we can design in MATLAB. And those filters are a lot like these eye goggles that just let the red color frequencies to pass through and all the other frequencies to block out. So that is kind of preview of coming attractions, so to speak, of the CT111. But for the time being, we want to look at the characteristics of the noise that the real world systems encounter. And it turns out that no matter which particular communication system it is, the additive portion of the noise has a signal component, the noise component, which are equally strong at all the frequencies. And so if I convert this loose notion of equally strong into something more specific, I would say that if I put a filter at one particular frequency and measure what is the power of the signal that I get at the output of this, then that power is the same as the power that I would get no matter where I put this filter. If I move this filter and go to another frequency and again record the power coming out of the filter, it will be the same as what I got at the first frequency. That is the concept of power spectral density. And for the white noise, just like how it is for the white colored light, this power spectral density is constant. And its value is N naught. It's denoted as N naught. So what this says is x-axis is frequency And the level of the y-axis tells me that if I put a filter here, a very small filter, which just passes this much portion of the spectrum and blocks everything out. And now if I measure the power, it will turn out to be N naught. If I go over here, I don't know how to change the color. Okay, so if I go over here and put a filter here, a very small filter, narrow filter, and again measure the power that comes out of this filter, it will still be same value. It will be equal to N naught. So that is what is meant by the white noise. Its spectral characteristic is very much like the white colored light. And the strength of the noise at any particular frequency is denoted as N naught, which is what the power spectral density is. Okay, so that was just a very quick note on the power spectral density. Now we are going to again kind of using the same conceptual framework. We are going to start looking at more advanced modulation schemes. So you will see that we will use exactly the same framework as before, but we will be able to appreciate more commonly used modulation schemes. BPSK is very good. It's very simple. It's very easy to understand modulation scheme. But in today's system, when there is a demand for higher and higher data rate, there is a need for going above and beyond BPSK. So that is what we are going to look at. A limitation of BPSK is that it's a one-dimensional modulation. Okay. Why it is one-dimensional? Because if I draw the constellation diagram, the two symbol points, I can connect a line through them. And for BPSK, that line passes through the origin of that plane. But then can we generalize to a 2D modulation? It turns out that we can. And then the resulting modulation is called quadrature phase shift gain. So you will notice that this quadrature phase shift gain has the same two constellation points as BPSK on the real valued line. But then I additionally stuck in two another constellation points which are perpendicular to the original constellation points. Okay. Now, the way now I would like you to start thinking about this plane on which we have drawn this constellation diagram, I would like you to think of it as a complex number plane. You are familiar with the notation of complex numbers. So this is x-axis is the real and y-axis is the imaginary. And so this will be just 1. Then this point will become what? You can tell me in terms of complex numbers. This is 1. What is this?
I.
I, sir.
I, sir.
I or j?
I.
In physics, you use notation I. In communication engineering, we use notation j for square root of -1. Then this is obviously -1 and then this will become minus 3.
-3.
And then this is the real valued line. So real. But in communication engineering, we sometimes also call it in phase. It's just a terminology, okay? Why it is called in phase, we don't need to worry about it too much. And this y-axis is imaginary, or it's sometimes also called as quadrature phase. And therefore, this diagram is sometimes called the diagram in the IQ plane, in phase and quadrature. So this is called IQ plane. And so in terms of the IQ plane, you will notice that this quadrature phase shift thing is actually just 2 BPSK signal. I have put one BPSK along the real, another over the imaginary. It's like I'm doing 2 BPSK together. Now, there is no reason that I have to put 4 symbols only at these 4 locations in the IQ plane. I can rotate them by 45 degrees and I can put them like this. You will notice that there is a difference between this diagram. The 4 points are 1, j, -1 and -j. Over here, I can't write them simply as 1j, -1, -j. They will have both real and imaginary components. But our concept still remains that the distance from the origin is going to be square root of the energy per symbol. Okay. Now, this QPSK has 4 symbols, twice of BPSK. And therefore, for BPSK, I had only 2 symbols, and so that to select one out of the 2, I just need 1 bit. For QPSK, how many bits would I need to select one of these 4 symbols? 2 bits.
2.
The answer is 2 bits, correct. So maybe one possible arrangement is that if I get 2 bits as 00 coming out of the channel encoder, then I transmit this particular constellation. If I get 0, 1, or rather I would say 1, 0, then I transmit this constellation point. This I would transmit if it is 1, 1, and this I will transmit if it is 0, 1. So you see that using QPSK symbol, I am able to transmit twice as many bits. One QPSK symbol carries 2 bits. And so now this energy per symbol is not going to be energy per bit like how it was for BPSK, but instead of that, it is going to be equal to I'm transmitting 2 bits per symbol. And so energy per symbol is going to be 2 times energy per bit. When I transmit a particular symbol at certain energy, at E of S, because I'm sending 2 bits, on a per bit level, I'm sending only half that much energy. Okay, so how does this QPSK scheme work? What I just wrote here, people call it as a mapping table. So QPSK will have this type of bit to symbol mapping. Remember, this is very much similar to the bits to symbol mapping that we had for BPSK. There it was very, very simple. X is equal to 1, we map it to plus A. X is equal to 0, we map it to minus A. How about QPSK? Well, QPSK, it looks a little more complicated, but once we understand what we are doing, it's not difficult to set it up. So, oh my God, all the handwritten part is gone. I think there's this subtlety of PowerPoint which I didn't realize before. So sorry about that. So what will happen is when I store this PowerPoint as a PDF, you will not see any of this handwritten part that I added, but at least in the video you will be able to see it. And starting from the next lecture, I will be careful to not lose, even in the PDF, this handwritten part. Okay, so for QPSK, now you look at 2 bits at a time, X0 and X1. And what this mapping table is telling us is that if X0, X1 is 1, 1, we set in phase and quadrature both to A divided by square root of 2. So which symbol are we transmitting when it is 1, 1? When
All in first quadrant.
correct. So with 1, 1, we are actually transmitting this particular symbol. Okay, then 1, 0, which symbol are we transmitting?
Fourth quadrant.
This is 1, 0. And this is 0, 0. This is 0, 1. Right? Now, you may be wondering, how do we transmit a complex number? So again, remember, this is a simplified model. When we actually convert this simplified model into an operational model, we will very clearly see how the complex numbers can physically be realized by the transmitter. For the time being, you just see what is going on in terms of converting bits to a complex number. Right? So the complex number corresponding to this is always SI plus J times SQ. This is the complex valued symbol. Okay, so that is what I have written here, that you can alternatively think of it as a 2-dimensional vector, SISQ, or as a single complex number, SI plus JSQ. So that is what the transmitter does for QPSK. Now let us see what the channel does. It turns out that the channel is always going to be like the villain of a movie. If you transmit only in the in phase, like the way it was in BPSK, it will put noise over there. So if you transmit in the quadrature phase along the imaginary axis, you can't hope that there will not be any noise. In fact, there will be equal amount of noise over there. And so now the noise affecting this transmitted symbol is also going to be 2-dimensional. And it's going to be equal in terms of power or energy in both the dimensions, in phase and quadrature. Basically, the noise doesn't care. It's going to be there. It doesn't care whether you are transmitting on in phase or quadrature phase. The noise is there in both the dimensions of this IQ plane. And so now the received vector R, if you consider it as a vector, it is going to be the sum of these two vectors, S and N. S and N and R are all two-dimensional vectors. Or in terms of imaginary and real and imaginary numbers, so in phase and quadrature, R of I is going to be is equal to S of I plus N of I. And R of Q, the quadrature part of the received voltage, is going to be S of Q plus N of Q. And so just like what we did for BPSK, we can draw the diagram that will happen at the receiver. Right? Remember, for BPSK, we just had this much portion of the diagram. For QPSK, we are transmitting along the quadrature axis. And so we have this other part present also. Is this fine?
Sir, I was having a question.
Sir,
Okay.
Divya, you had something to say?
Yes, sir.
sir, in
It will be
binary
scattered circularly
BPSK,
around.
we have linear means the noise is heavy linear, but in this case, noise can be in any direction.
Uh-huh. Good, Divya. Okay, fine. Vandan, do you have any question, comment?
Yes, sir. I am telling that in BPSK we have only one direction in which we can have noise, but in this case, the noise can be in any direction.
Yeah, so there's something missing in this diagram, that the noise vector, like both Divya and Vandan mentioned, it spreads out in all directions. What is the problem with this diagram? That all these noisy vectors here, all of them have as NQ is equal to 0. And they have only Ni non-zero. Whereas all of these blue dots, for them Ni is 0 and NQ is not 0. Right, so this applies to all of these points, whereas this here applies to these points. But as what several students have mentioned, the real world noise is not like that. The in-phase noise doesn't care what the quadrature is, and vice versa. So they both occur independent of each other. This is highly dependent scenario. It's as if the quadrature noise here says that, okay, in-phase became non-zero, so I have to become 0. In this case, it's like the in-phase noise says that, okay, quadrature is non-zero, so now I have to become 0. There is no such connection or dependence in the real life between in-phase and quadrature noise. And so the received constellation diagram actually looks more like this. Or in this alternate arrangement that we have considered, it will become a cloud like this. So now we can again do the minimum distance decoding. And this again assumes that all these 4 symbols of QPSK are equally likely. That probability is 0.25. So assuming that all the four symbols are equally likely, which by the way also is a corollary of Q being 0.5 for X. Incoming bits, if the zeros and ones are equally likely, then again, all four symbols will also be equally likely. So with that as the underlying assumption, suppose now at the receiver, if I observe this particular received vector in the IQ plane, then by the principle of maximum likelihood or the principle of distance minimization, which of these four transmitted symbol I will consider as the most likely to have been transmitted?
E4.
With minimum
Vec-
distance.
It will be
Vector
this
length
symbol.
small.
Yeah, it will be this symbol because the length of E4 is smaller than E1 and E2 and E3 lengths. So again, very easily we are able to extend the receiver design, the optimum receiver design, the maximum likelihood receiver design for QPSK by just fully understanding how it works for BPSK. Now, in
Sir?
BPSK, we drew the decision boundaries. How will you draw the decision boundary for this constellation, for QPSK?
Sir, at
Can
an
draw
angle of 45
We
degree on
have
both
to
sides.
two
We
straight
will
lines.
draw circles with center.
No,
Circle
sir. It will be
centers.
four straight lines which will
We will draw four quadrants.
divide
Line
the
with
plane in
45
four
degree
equal
and
parts.
Yeah, it won't be circles, but others
Sir,
are
at an
saying
angle of 45 degree on both sides.
correct. It will be
Symbol.
45-degree angle on both the sides. So this is how it will look like. Here I increased the noise level in my simulation. And so this clouds became like a complete circular cloud. And then the portion of the cloud that lies within this region, the red colored ones, I will always decode it as this symbol. And so on. So I color coded the decision regions. What about the decision boundary for this particular constellation? This one over here.
X
So
axis
it will
and
be four
Y axis.
quadrants.
This will be simply four quadrants, correct? So you will see that the difference between these two constellations is that one is 45-degree rotated version of the other. And so obviously the decision boundaries also got rotated by 45 degrees. Here, maybe we do one last thing. So now that we have understood this, we can actually again kind of go great distances. If you are walking, maybe in 1 minute we can walk maybe only 10 meters or 20 meters. But if you are in a car, in 1 minute we can maybe go as far as, I don't know, half a kilometer or something. And so that way we will now be able to travel quickly. Let's consider one more modulation scheme, which is known as binary frequency shift scheme. Here, bit 0 is transmitted at some frequency and bit 1 is transmitted at some other frequency. And it turns out that these two frequencies actually become perpendicular to each other. In a way, this is like BPSK. We are transmitting only one bit. But unlike BPSK, we are putting the symbols on two perpendicular dimensions. And so once we define the symbol constellation, we can draw even the decision boundary at the receiver. And it looks like this. So this is bit 0. This is bit 1. Instead of energy per symbol, now I'm back to energy per bit because symbols and bits are same in this case. But the constellation points have different coordinates. Here it is square root of EB 0. Here it is 0 square root of EB. This is definitely not 1D. This is a 2D constellation because I need two perpendicular axes. Alternatively, if in a way, you may say that it's 1D because I can connect these 2 points by a straight line. But it still is not 2D because this straight line doesn't pass through the origin. And then finally, decision region R1 is going to be on this side of the red line. R2 is going to be on the other side of the red line. And the red line is nothing but the perpendicular bisector of this black line that I have drawn.
Sir, what do you mean by perpendicular frequency?
Yeah, so this is frequency F1. This is frequency F2. If your question is how can I draw these two frequencies perpendicular to each other, again, park your question, okay? We will come back to it in a future lecture. For the time being, just accept what I'm telling you.
Sir, it's like a EM wave where both electron and magnetic wave are perpendicular to each other.
Yeah, in fact, you can think of it sort of like that. But the other way to think of it is also more general, that we will be thinking of this EM waves. I mean, they are actual signals, they are physical wave fronts. We will start thinking of them as vectors. So the EM wave at frequency F1 is one vector, frequency F2 is another vector. And we will see that these two vectors are literally perpendicular to each other.
So is it connected to the phase with which we are transmitting the signals?
No. But when I say that the vectorial representation of these two signals, in that the two vectors become perpendicular to each other, what does it mean? When are the two vectors perpendicular?
Phase difference 90 degrees.
Yeah, I mean that you are just telling me what I asked you. Perpendicular does mean 90 degree, but when are the two vectors
Dot product 0.
90 degree?
Dot product 0.
Yes, Pujan, that is the right answer. If we take dot product of two vectors, if it is non-zero, we say they are not perpendicular. If it becomes 0, then we say they are 90 degree apart. And so in that sense, we will find that the EM wave corresponding to F1, once we start looking at it in terms of a vector, we'll find that its dot product with the EM wave at F2 is becoming 0. That is also the case for this type of constellation diagram. We will be actually transmitting an EM wave corresponding to the quadrature, another EM wave corresponding to the in phase, and their dot product also we will show that it becomes 0. So there is a nice underlying kind of unification with linear algebra here actually. This is not some random diagrams that we are just, okay, because we can't think of anything else, we just draw two perpendicular lines. It is not like that. This is actually intimately connected to the signals that get transmitted by your phone, that travel over the air or through your landline cable or anything. There is a very nice and very elegant way of thinking of those signals as comprised of linear superposition or linear combination of two orthogonal EM waves. And by orthogonal, what I mean is that if I take some type of dot product of these two EM waves, that dot product always is 0. And so I think somebody was saying that, what about this electric field and magnetic field? Yeah, they are like that. If you take dot product of those two, it will be 0 because they are 90 degrees apart in the phase. But here we will be generalizing that concept. And when I say the actual transmitted signal is a linear superposition of the two EM waves, that is what it is doing over here. This particular constellation point is a linear superposition of the EM wave in phase and quadrature. And what is that linear superposition? That is exactly what that mapping table gave us. Okay, so this is where we are going to stop today. I think when we meet again on next time, we will find that we are going to be able to come to grips with